In the previous video, we saw how to construct Tukey confidence intervals using the plane risk data that we've been working through. I'm going to now talk about constructing Bonferroni. Remember, you're not going to construct both of these. You're going to choose. And your choice is going to be based upon considerations such as, do I have homogeneity of variance? Both Tukey and Scheffé require homogeneity of variance. We do not need homogeneity of variance to do Bonferroni. Now, if I go back up and look at my plots up here and also my standard deviations, if you were concerned about the fact that you had different standard deviations for these different conditions, then you might want to stick to Bonferroni and do Bonferroni. If you do the omnibus first, now remember the omnibus does assume that you have equal standard deviations, and if you do the omnibus first and it does not reject, then you don't go on to any of the procedures, you stop there. But if you do reject the null hypothesis of mean equality, then you can move on. Alternatively, you could look at these and say, I'm not happy with how dissimilar they are. Now, I've pointed out to you before that studies have shown that if you're not more than one of them more than two different than another, you're probably going to be okay. But if you're real conservative about this and say, that's not close enough for me, I do realize about sampling error and that the populations might have the same variances and we still get these kind of results, but I want to be real careful. Well, if you want to be real careful, you could just skip the omnibus and go right to Bonferroni. If you're doing Bonferroni for all pairwise, the only reason you would do that is if you do not have homogeneity of variance, because Tukey is going to be more powerful if you do have homogeneity of variance. If you have homogeneity of variance, you can still use Bonferroni, especially if you're not going to do all pairs. Now, I'm going to go ahead and do all pairs now, so that would assume that I believe that maybe I don't have homogeneity of variance, and so I would do Bonferroni instead of Tukey in this case. So let's see how to set this up, and we'll be able to see why it is we don't need homogeneity of variance. So I'm going to go ahead and put the code for all three of these in here, and then we'll talk about it. So we're going to do t-test. We're going to do three different t-tests. And even though the traditional method of doing t-test relies also on homogeneity of variance, the people who program R are a little bit more progressive than that, and they have actually programmed in an approximation, an adjustment that allows you not to have equal variances. So that's why the t-test in R doesn't require equal variances. So notice what I've done here. This is the response variable as a function of the explanatory. No difference there, except that you notice I don't put the plane risk in front. That's because I'm showing you another feature here. We can set the data equal to plane risk. Now, alternatively, what I could have done is taken that out and put in here plane risk $ score and plane risk $ view. But notice it's a little bit more efficient to just go ahead and put in score and view and indicate that our data are the plane risk data. So we put that in as an argument for our t-test function. Then down here what I'm doing is I'm pulling out only the individualist and the hierarchicalist. Because if I'm doing a t-test, the assumption is I have only two groups. If I don't do this little subsetting function, then it's going to give me an error message. It's going to tell me I have more than two groups. So what I'm doing is saying, hey, the view variable needs to be set equal to, or we need to pick out when it's equal to, and that's the double equal sign. If I had a single equal sign, it would say set view equal to individualist. Double equal sign means is view equal to individualist? Is view equal to hierarchicalist? And if it's individualist or that's that little bar, it's hierarchicalist, either one, pull it out and use it in the data. So what this is going to do is it's going to eliminate egalitarian. Okay? And then remember the alpha over C? Here it is, right here. Alpha, 0.05, divided by C, the number of contrast is 3, and my confidence level is going to be 1 minus that. Each of these other ones are a repeat, except that we're doing two different comparisons. This one's individualist and egalitarian, and this one's hierarchicalist and egalitarian. So if I run all of those, not only will I see my difference in means, or my actual means right here, and that should match what we got. Let's see, 38.96 for the individualist. Let's go way back up here. There it is, 38.96 for the individualist. So we're recalculating those means. But not only will it give us those means, it will give us a confidence interval for the difference in means. And what order am I subtracting? Whatever is named first minus whatever is named second. So if you want to force the order of subtraction, you can do that up here when you set this subset by putting, in this case, I put individualist first, so it's going to subtract hierarchicalist from individualist. And I like that actually, because that will give me my positive numbers I was hoping for. Here is the positive number here of 1.6 to 26.4. That's individualist minus egalitarian. This again is a confidence interval. Now you see up here it says 98.33. That's fine, but the reason it says that is because you want each of these to be 98.333 so that you can say I'm 95% confident in the set. And that's typically what we do. We don't typically say, here's my 98.33% confidence interval. What we say is, here is the set of confidence intervals for individualist minus hierarchicalist, negative 10.2 to 14.3. For individualist minus egalitarian, 1.6 to 26.4. And for hierarchicalist to egalitarian, the difference is 3.1 to 20.9, and I'm 95% confident in the entire family of comparisons, meaning that you have only a 5% chance of any of these being wrong. You're 95% confident in the entire set all at once. So that's how we do this. Now, what if we had wanted to only do two comparisons? Now, remember, Tukey, you do all pairwise, but what if you only wanted to do two comparisons? Let's say, for instance, I'll just temporarily remove this. I'll put it back in after we're done. But let's say I just wanted to do these two comparisons. The only thing that changes here is this 3 would change to a 2. And notice how that's going to give you narrower confidence intervals. If I were to run these, let's look at individualist and egalitarian down here. Before we got 1.6 to 26.4. 1.6 to 26.4, remember that. This time I got 2.4 to 25.6. See how that's a narrower interval? Why? Because I did not break up alpha by as many contrast as I did before. So I'm going to go ahead and switch this back to 3. I'm going to go ahead and put this back in. And so that we'll have this saved the way we actually did it. And that's it for Bonferroni. That's how we construct Bonferroni confidence intervals. We just do repeated t-test with an adjustment on alpha depending upon how many of these we're going to do. And one of the main features is we don't have to assume that we have the same variance in each of the groups. In the next video, we'll look at Chiffé.